How's it going, everyone? Welcome back to another video. Today we're going to talk about speed versus velocity. In physics, when we are defining these two terms, they have a small distinction between the two, but it does become important depending on the type of physics that you're working with. When we talk about speed is more familiar. It's just how fast something goes. The physics definition we're going to work with is speed is a scalar quantity that refers to the rate an object covers distance over time. Whereas velocity is a vector quantity that refers to the rate an object changes its position over time in a particular direction. So we talked about in another video scalar versus vector quantities. Scalars just means it's just a measurement. Doesn't matter the direction of what it is. It could be like calories, degrees, speed, distance. But a vector quantity implies that the object has a particular motion in a particular direction, or at least if we're covering distance, the distance goes into a particular direction. Mentioned in a previous video, we talked about the difference between distance versus displacement. When we're talking about distance, that's just the entire amount of ground that an object is covering, whereas a change in its position, we're talking about displacement. So how far from an original position did an object move over a given amount of time in this case. Let's go ahead and look at the equations that we'll be working with for this and solve a couple problems. Okay, the equations that we use for speed and velocity are basically the same for each other. It's a amount of ground that's being covered over a given amount of time. So in speed's case, we're looking at distance, so it's the total ground that an object is covering. In velocity's case, though, we're looking at displacement. So the starting position versus the ending position, those change in original starting and its finishing positions over time. And we want to know the direction that that object moved, whether it moved right, left, north, south, whatever we're working with here. Let's go ahead and take a look at our first example here. All right, here's our first example. Usain Bolt currently holds the men's world record for the 100-meter dash at 9.58 seconds. That was set back in 2009. While Florence Griffith Joyner currently holds the women's world record for the 100-meter dash at 10.49 seconds. What was their average speed for this event in meters per second? Now, this is not going to be their top speed. This is for the average speed that they had. They were probably going at least a little bit faster than what we're about to see here, which makes it even sound more impressive. But we're asking for speed. Let's go ahead and we'll write out the equation here that we need, the formula. S equals distance over time. We want to know the speed, so we will just leave that blank here, and we'll use the S as our variable that we're trying to find for math-wise. Distance is equal to, well, this is a 100-meter dash, so it's 100 meters. And time for Usain Bolt was 9.58 seconds. And then the time for Florence Griffith Joyner, Florence, was 10.49 seconds. Okay, try and figure out their speeds. We just plug this information into this formula here using this. Let's see, your distance was 100 meters, so we'll go S. We don't know S. 100 meters there. Over Usain Bolt's time we'll find first. It was 9.58 seconds. And then we just go 100 divided by the time. Get out my calculator here. 100 divided by 9.58. I'm sure I could have done this in my head if I really tried. No, probably not. Usain Bolt was moving at about 10.44 meters per second on average. He was moving a little bit slower in the beginning. He was probably moving faster at the end, but that was Usain Bolt's speed. And we want to know Florence Griffith Joyner, her speed. So we just do the same thing. So put a U there for Usain Bolt and F for Florence. Same distance, it was 100 meters. plug in her time, which was 10.49. And same thing, we go 100 divided by 10.49. That's just going to be a little bit less. Her speed was 9.53 meters per second. Now, for this particular problem, if we were trying to find their velocity, we would need to know their displacement. And it's really helpful to, if we're trying to figure out what the displacement is, to draw a diagram here. So this is where they're starting at right here. Let's draw a little picture right here. There's Usain Bolt getting ready to run. And there's the whole track. Finishes here. This whole distance right here is 100 meters. They don't come back at all. They finish right there between the start and the finish line, right there at the finish line. So their distance is also equal to their displacement. And since the velocity is equal to displacement, over time, you would get the same answers. Their speed in this case would be the same as their velocities. Let's go ahead and look at another example. Okay, here's our second example. We have a car traveling at 75 miles per hour on the freeway. It's heading east until it has traveled a total distance of 223 miles. How long will it take to drive this total distance? So we'll just, same thing, we'll write our equation out, and its speed is 75 miles per hour. Its distance it needs to travel is 223 miles, and we need to know the time, so we'll leave that blank there. Let's go ahead, plug this information into our little formula here for speed. So for the S, we'll plug in 75. For the distance, we'll plug in 223. And then for the T, we'll plug in a T. Now, there's a couple ways to go about this. This is all kind of late elementary, middle school, early high school type of math here. I'm going to show this in the way that it works best in my head when I try to solve these problems. The trick to solving this, you need to get the T by itself. And the way you get T by itself here, one way is to divide by 75 here. And that will end up getting you your answer for T. But that ends up putting T over here, and it's not really as intuitive here, so you would go 223 divided by 75. And that would get you 2.97 hours. The way I was always taught is you got to get the T by itself, but how did the T get over here? And if we put this over here, why does that work? And there's some math involved there. So I like to do it a different way, and I'll just kind of show that really quick here. So instead of just straight dividing by 75, if that's just not something that works in your head, you can't remember that on a regular basis, what I would do is just multiply T to both sides. So that way we're not dealing with something that has a denominator that's a variable there, and that gets a 75T, gets rid of T on this side. And then we see where we get the divide by 75. So in order to get T by itself over here, we just divide by 75, and that gets us T over here. And it should be the same thing. Well, it's 2.97. This was miles per hour. This was miles. That's hours. Man, that's a long time driving. If this distance happened to be the same displacement here, of 223 miles, it would be the same thing. You would just plug in the displacement as well, follow the same format, and that would also get you the time if you wanted to know its velocity. And for this, we would assume speed is the same as velocity. Let's go ahead and do one more problem. Third example, we're going to do one more quick example over there. I want to do a example where the speed is different from the velocity so we can see an example of what that looks like. But here in our third example here, we got an airplane is traveling from Seattle, Washington to Miami, Florida, traveling at an average speed of 583 miles per hour. The time by flight to get from Seattle to Miami by plane is on average 5.7 hours long. I looked that up just like Googling it really quickly. If it's any faster or slower, don't quote me on that. What is the total distance covered by the plane during this flight? Okay, so let's plug in everything that we know here. So, we're trying to find the distance. So we're trying to find the distance. We'll leave that blank. Speed is 583 miles per hour. Got that from just looking up about the average speed of a Boeing 737. Average time is 5.7 hours long. And what's about the total distance that plane covers, given this information here? So plug them in. Same thing that we did before. Speed is equal to 583 miles per hour. That equals 5.7 hours. Distance, excuse me, over 5.7 hours. Let me get rid of that just to make it cleaner. Okay, we're trying to find the distance here in this case. To get distance by itself and figure out what that is, we got to multiply by both sides by 5.7 times 5.7. This cancels out the 5.7 that was dividing distance, and bring that down here. Distance is equal to 0.7 times 583, 3,323.1 miles. Roughly, give or take maybe 100 miles or so. Okay, let's go ahead and look at just one more example. An example where throughout the same race, maybe the speed might not necessarily be the same as the velocity, given that distances and displacement are not the same. Okay, here's our example. We have a really fast person running 300 meters on a track in 45.8 seconds. Maybe that's not so fast, but I mean, maybe they're just jogging. It's a warm-up really quick. What is that person's speed and velocity? So if we take a look at a track here, let's say they're starting over here at the normal 400 meter starting spot, and they just wanted to finish over here at the 100 meter spot right here. So here's start, here's finish. They run around the track right here. Well, let's go ahead and write this out. We need to find the distance, speed, and time here for this. And for velocity, we need to find the displacement and time so that we can find the velocity. This person starts here, they run around the track here in this route, and they finish right here. This is the total distance that person covers. They ran around the track. That was the ground that they covered. If you draw a line, that's the path they took. That's how much ground they covered. So we would write 300 right here. Now their speed is what we're trying to figure out. This person took 45.8 seconds to do that. Okay, displacement. Again, if we're trying to find the velocity, we need to know their displacement. That is just a change from their starting position to their finishing position, wherever their path, regardless of the path that they took to get there. So we have a person right here, runs around the track, finishes right here. We ignore the path that they took, and we're just concerned with here to here. That distance right there, or displacement, excuse me, is 100 meters. So for the displacement, we would put 100 meters. Time it took was still the same. And because this displacement was, well, if we're just going from our image right here to the left, it is 100 meters left of their starting position. Now we just plug this in and solve for it. So speed is equal to distance over time. Plug in 300 divided by 45.8, and that is going to equal about 6.55 meters per second. And then we do the same thing here. We got velocity is equal to displacement, 100 meters over the same amount of time. And that's going to come out to 2.18 meters per second left. Left because that's where they finish, and velocity is a vector quantity. We're concerned about the direction that they move, and it goes much slower because this is the only ground that we're tracking here. This person started here, finished here. That is the only thing we're concerned about. While he's appeared to be running way faster here speed-wise, in terms of his motion, his change in position, he wasn't really moving that fast. I hope you found this video helpful. Thank you for watching. If you found it helpful, please leave a like, subscribe to the channel. It helps a lot. Make more videos in physics, biology, chemistry in the future, and I'll see you all in the next one. Thanks for watching.